Yes, 2025 was the International Year of Quantum Science and Technology in celebration of the invention of our strangest true theory 100 years ago. In 1925, quantum mechanics went from being a peculiar set of ideas to describe some funny results from experiments to a full-blown theoretical framework that overturned how we think reality really works. So, today, as the centenary year approaches its end, I want to take you on a little journey through what may have been the most paradigm-destroying several months in scientific history. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Now for the fun part. It's holiday discount week at the Spacetime merch store. From now through next Friday, you can get 20 to 50% off most merch items from all of 2025, including limited restocks and 4 new releases. First up, with the LHC Higgs Discovery desktop and gaming mat, this 32-inch by 16-inch mat with anti-slip design was inspired by the discovery of the Higgs at the Large Hadron Collider. Plus we have our final shirt and hoodie of the year, Don't Panic, It's Only Rocket Science. It's one of our rare full-color designs inspired by a little restaurant at the end of the universe. There's a link in the description. Now onto the episode. Let's start by understanding where we stood at the beginning of 1925. What was the scientific worldview that was about to be shattered? So, Albert Einstein has been the king of physics for a decade, ever since he published his general theory of relativity in 1915 and toppled the 4th century reign of Newtonian mechanics. GR completely supplanted our understanding of space, time, motion, and gravity. This was a revolution, no doubt, but in a way, Einstein actually reinforced the status quo rather than overturning it. See, in the Newtonian worldview, the motion of all particles could be perfectly computed through a simple set of universal laws. And all things are made of particles, so surely then the universe itself and all it contains is computable. It's all deterministic. Know the present and you can calculate all past and future states. Newton's achievement gave us a sense that the universe is knowable to a degree of completeness never before imagined. There were some few inconsistencies remaining. The fact that Mercury's orbit didn't quite obey Newton, some stuff about electromagnetism and the speed of light. But the universe has to be axiomatically self-consistent, and so Einstein was able to leverage these seemingly minor glitches into a full-blown scientific revolution in which space and time were merged, and the resulting space-time was no longer Newton's static universal background, but rather a malleable, dynamic thing. But the new picture that came out of Einstein's relativity still shared a fundamental quality with Newton's worldview. It was just as deterministic. The equations of general relativity suffer no uncertainty. The distribution of matter and energy in spacetime perfectly defines the geometry of that spacetime, which in turn completely determines the motion of said matter and energy, forever into the past and future. Einstein also showed that simultaneity is relative, destroying our delusion of an absolute sense of now. So the already deterministic past and future became as real as the present, at least in some interpretations, and all of time was sort of crystallized into an eternal block for the entirety of existence. On the one hand, the universe under Einstein remained measurable and knowable, but what is measured and what can be known came to depend on perspective, where you are, how fast you're moving, the light speed limited horizon of your embedded vision. A hell of a perspective shift, but still firmly on the side of determinism. In the early 1920s, Einstein was a science rock star. Now, there were still a few loose threads in the fabric of our understanding of the world, so you can imagine the hunger of a young physicist of that era to pull on these threads and to perhaps pull off another revolution. Now, a big outstanding mystery, and perhaps the big one, was the strange world of the atom, and especially the behavior of the humble electron. From Rutherford, we knew the rudimentary atomic nucleus. You've all seen depictions of electrons whizzing around the nuclei like tiny solar systems, a holdover from early assumptions that the tiny universe resembles the gigantic. But there were so many questions. Why were only certain electron orbits allowed? And why those ones? And why didn't electrons spiral into their nuclei? The uncanny orbit of the electron was surely the key to a new revolution, just as the orbit of Mercury unlocked relativity. The first steps were tentative. Niels Bohr, building on Planck and Einstein's quantization of light, gave us an empirical model of the quantized electron energy levels. Louis de Broglie, building on that same quantization, guessed that all of matter had to have a wave nature. Bohr then realized that these electron waves made sense in his atomic model. The allowed orbits are those that perfectly fit an integer number of electron wave cycles. These are self-reinforcing standing waves. While this gave a nice story for the quantization of electron orbits, other problems remained, perhaps the worst being that this only worked for the humble hydrogen atom. So that's where we stood going into 1925. Bohr's model was still very classical feeling, and so Newtonian and Einsteinian worldviews still reigned. We clung to the ambition to be aloof masters of a computable universe. The spark that set this entire worldview ablaze had already started in Munich a few years earlier, when a 20-year-old student showed up in the office of Arnold Sommerfeld. Sommerfeld, famous both as a physicist and for his mentorship, handed that student a trial problem to solve one of the many failings of the Bohr model. In particular, the distortions in hydrogen energy levels seen when the stuff is in strong magnetic fields, called the anomalous Zeeman effect. So the thing about being a kid is you'll try anything. You don't know what you're supposed to take as ground truth. All common sense dictated that the math should be based on integer numbers, the whole numbers of wave cycles in Bohr's electron orbits. But Sommerfeld's naive student, for whatever reason, tried a mathematical form involving physically irrelevant half integers, half one, one half, blah, blah, blah. But that worked. The student was Werner Heisenberg, and at 20 he discovered the first clue to the strange phase symmetry of the electron, a result of its yet undiscovered quantum spin. This little project began Heisenberg's obsession with the mysteries of the atom. 3 years later, now 1925, Heisenberg was in Göttingen, studying under Max Born, but also in close connection with the now very famous Niels Bohr, his future closest collaborator. Surrounded by such a giant of physics, Heisenberg still turned to the wisdom of Einstein. Heisenberg asked himself, what would Einstein do? In coming up with general relativity, Einstein had resolved to reject unfounded assumptions, no matter how self-evident they seemed. That meant putting aside Newtonian ideas like the universality of time and an unchanging and flat geometry of space. So Heisenberg challenged himself to take that credo seriously and to push it as far as possible. In his own words, the aim of quantum theory should be to describe only quantities which are observable. Make no assumptions about, for example, what the electrons are really doing inside the atom. Instead, build a theory entirely around the results of what we see when we do measurements on the atom. In a cartoon view of an atom, you can imagine knowing things like where the electron is or how fast it's moving at any point in time. In the Bohr model, that translates to a radius and energy/momentum for each of those orbits, a pair of concrete values, each with an index to connect them to a list of possible electron states. But Heisenberg realized that it's not possible to actually observe these orbits of the electrons within the atom. The only thing we can measure is the light, the photon, that shoots out when an electron changes orbit. In fact, even the idea of orbits is presumptuous, so we'll call them electron states. These invisible electron states couldn't be the main players in the theory. Instead, Heisenberg committed to finding a law of motion that only describes the observables, the frequency and intensity/amplitude of the photon produced when electrons change states. The difference seems subtle, but it really changes everything. Instead of a formula to describe electron properties for a single list of states, Heisenberg sought a formula to describe the resulting photon properties for every combination of initial and final state of the electron. Now, this sort of two-index list of properties is known as a matrix, although Heisenberg didn't know it at the time. His job was to get a formula relating these matrices, and so he figured out the algebra of matrices all on his own. He was disconcerted to discover something that mathematicians already knew, that matrix algebra defies standard multiplication rules. For example, x times y is not always the same as y times x. They are, as we say, non-commutable. This turns out to be a central feature of quantum mechanics, and ultimately it led Heisenberg not only to his solution, but to the thing that he's most famous for, his uncertainty principle. But for now, this unintuitive type of math was just another challenge to Heisenberg's resolution that he should reject prior assumptions. And so he forged ahead. Now, his theory needed to do a couple of things. It needed to predict the photon frequencies and intensities, or the spectra of atoms. It also needed to be consistent with certain known fundamentals of the universe. And the big one is the principle of energy conservation. Heisenberg writes that he knew only too well that my scheme stood or fell by that principle. '25. It's just the beginning. It's already. So Heisenberg tested his theory as simply as he could.
I saw her in the pre-game lobby and I was like, I know I'm going to die to a Kim K. It's always a Kim K.
Chosen for some mathematical conveniences. If energy conservation held in this case, then his strange theory must be connected to the true machinery of nature. Now, this was in May 1925.
I don't think I prefer the chaos anymore.
Was awash in springtime pollen, and so Heisenberg's own immune system tried to kill him. He had a crippling attack of hay fever. It swelled his face, weakened his body, and left him barely able to multiply a matrix. He begged his boss, Max Born, for permission to travel to the one place he might find relief, a small, barren island in the middle of the North Sea, called Helgoland. It's an amazing place, Helgoland, sometimes also Heligoland, from the High Frisian Holy Land, with its stunning ocean cliffs and elegant resort town. Now, the war changed all of that. The town was obliterated by Allied bombs and a Nazi U-boat harbor, and the entire tip of the island was destroyed in the largest non-nuke man-made explosion in all of history. But Heisenberg came before all of that. He spent 10 days walking the cliffs, swimming the ocean, and calculating his matrices. Pages upon pages of them. He talks about a mounting excitement as the scheme remained self-consistent of how that excitement led to many mistakes that he had to fix. And then finally, on the night of June 9th, 1925, well, let's let Heisenberg say it. It was 3 o'clock in the morning before the final result of my computations lay before me. The energy principle had held. At first, I was deeply alarmed. I had a feeling that through the surface of atomic phenomena, I was looking at a strangely beautiful interior, and felt almost giddy at the thought that I now had to probe this wealth of mathematical structures nature had so generously spread out before me. I was far too excited to sleep, and so, as a new day dawned, I made for the southern tip of the island and waited for the sun to rise. So, cured of hay fever, but now afflicted by revelation, Heisenberg returned to Göttingen. His friend Wolfgang Pauli encouraged him to show his work to Max Born. He immediately recognized Heisenberg's strange mathematics as being matrix algebra. From there, he worked with Jordan Pascal, and then with Pauli and Paul Dirac to flesh out matrix mechanics, the first complete formulation of quantum mechanics. But it was not the instant hit you might have imagined. It was a strange theory. Matrices were unfamiliar to most physicists of the era. The non-commutivity felt alien. But perhaps worst of all, the theory seemed to tell no story of what was really happening inside the atom, inside the electron. The catalyzing philosophy of only consider the observable was uncomfortable, but it did evolve into the Copenhagen interpretation of quantum mechanics, developed primarily with Niels Bohr. In this interpretation, the universe between measurements is unknowable, and not just in a practical sense because you didn't measure, but in the sense of being truly undefined. This is the key fracture in the old worldview of Newton and Einstein. Matrix mechanics implied that the world is not fundamentally knowable, perhaps not even real between observations in the concrete manner that we were used to. And any attempt at knowing was limited by Heisenberg's uncertainty principle, which he soon realized must follow from the matrix non-conductivity. And there's also the related randomness of quantum mechanics, which is kind of baked into the quantum laws of nature. All of it was a violent takedown of the deterministic and observer-independent Newtonian worldview. So physicists were eager to at least claw back some sense of realism, of a mechanism that's independent of observer and measurement. And a few months later, Erwin Schrödinger gave them exactly that. Where Heisenberg had launched his chain of thought from the quantization of energy levels, Schrödinger starts with de Broglie's idea of particles as waves of matter. Physicists had long pondered the connection between particles and waves, and there was even a formulation of classical mechanics, the Hamilton-Jacobi equation, that could represent particles as waves while still being formally equivalent to Newton's laws. In fact, Schrödinger just substituted the so-called action in this Hamilton-Jacobi equation with what we now call the wave function to lead to the famous Schrödinger equation. And in doing so, he established wave mechanics as a new way to formulate quantum mechanics. Apparently, seclusion in nature is key to quantum discoveries, because Schrödinger was on vacation high in the Alps in the Swiss town of Arosa when he made his discovery. He'd retreated there for the Christmas holidays with, as he reports, a stack of de Broglie's papers and one of his many girlfriends, whose identity to this day remains a mystery. So not quite as secluded as Heisenberg. Schrödinger may have come up with the final version of his equation in December of 1925, and so you may be watching this episode at the true centenary of the Schrödinger equation. But certainly by January 1926, the work was complete because by then he'd returned to Zurich and submitted the paper. So by the start of 1926, we had not one but two complete formulations of quantum mechanics. wave mechanics was an instant hit in the way that matrix mechanics was not. And that's thanks to the familiarity of the wave formulation versus the then unfamiliar matrix mechanics. Perhaps even more attractive, though, was the fact that the Schrödinger picture seemed to tell a story of what was happening behind the math. The theory described this continuous deterministic object, the wave function. It was something that you could imagine, something that sort of existed between observations. But this comfort wouldn't last. Although the idea of waves moving through space was familiar, Schrödinger's formulation couldn't tell us what these were waves of. Max Born then showed that the wave function could be thought of as representing probability amplitudes, the square of which gives us the actual probability of a given measurement. But what does a wave of probability even mean? Is it a thing that even exists, or a statistical map of underlying activity, or some wishy-washy epistemic entity that's uncomfortably tied to the observer? Schrödinger, and probably many others, hopes that the wave function would retain some kind of realist nature, a physical existence, but no fully consistent approach to such an interpretation emerged, nor has it yet. Regarding the probabilistic interpretation, Schrödinger wrote, "I don't like it, and I'm sorry I ever had anything to do with it. In fact, applying the Schrödinger equation directly to things like the double-slit experiment quickly told us that even this more realist wave mechanics had the same underlying principle as matrix mechanics. We can only know the input and output states. Everything in between is pure potentiality." And then, in 1927, Paul Dirac showed that the Heisenberg and Schrödinger pictures are mathematically equivalent. They really are two representations of the same system. They predict the same amplitudes. While wave mechanics did become more famous due to its intuitive advantage, the Heisenberg and Schrödinger pictures both have their roles, both are useful in different circumstances. But it's arguable that Heisenberg's picture is more general, closer to base truth. That's because the Schrödinger equation is inconsistent with special relativity. Relativity treats time on the same footing as the dimensions of space, while the Schrödinger equation assigns both space and time a primary and universal status, more like in Newtonian mechanics. Now, of course, Schrödinger knew that his equation was an approximation, valid only at low speeds. But the principle of the equation was right, and Paul Dirac would go on to publish a full relativistic version of the wave equation in 1928. But that's a story for another time. In fact, for a previous time, because we already covered it.
I knew he was going to.
Matrix
Let him die now.
Is perfectly consistent with special relativity. It doesn't treat time and space separately because it doesn't treat space at all.
I thought we were only
space is built into it. Where wave mechanics describes evolution through space, matrix mechanics describes evolution in something called Hilbert space. That's the space of states of the quantum system, which can involve spacey things like position and momentum, but can also be electron orbitals or spins or whatever. The same abstractness that makes matrix mechanics so daunting also frees it from the assumption Einstein.
That's hilarious.
Heisenberg's only the observables led him to a more general, if less straightforward, formulation of Schrödinger. And it's for that reason that Heisenberg's formulation also became the foundation for the next evolution of quantum mechanics, and that's quantum field theory. Following the crazy half-year from June to December 1925, a mad flurry of advances propelled this fringe idea into a full-blown description of the subatomic world. Now, I mentioned the Dirac equation, but then came second quantization via the Heisenberg picture that gave us quantum field theory, in which particles are excitations in fields shaped by the symmetries of nature, and that led to the standard model particle physics. The predictive power of that model has enabled so much incredible technology, but all of it was founded on the core principles that were set down in 1925 and have held true to this day. The world watched by quantum mechanics, the world of the International Year of Quantum Science and Technology, it's one of transistor-driven miracles from smartphones to satellites. It's one of quantum...
I don't really feel like talking to the guy, though. I don't feel like talking in general. I'm trying to multitask.
Chemistry, advanced materials, and nuclear power. 100 years of building useful things from century-old epiphanies. But it's also a world whose deepest layers are, if anything, less settled than in the previous era. A century later, we still don't know what quantum mechanics means, what story to tell about the mechanisms at play beneath the observables, if such a story can even be told at all. Questions like what exists or what can be known are no longer clearly answerable. One more Heisenberg quote. What we observe is not nature itself, but nature exposed to our method of questioning. There's a boundary between the external reality and our observations of that reality. Quantum mechanics makes us question whether even our most powerful theories can ever breach that boundary. It's been a giddying era of equally profound insight and confusion. So here's to a century of quantum mechanics, and while we're at it, to another year of space-time. Thank you to Novium for supporting PBS. Inspired by space, the Novium Hopper Pen Interstellar is an otherworldly gift idea for yourself or the amazing people in your life. Pretty cool. The Hover Pen Interstellar is available in Space Black, Starlight Silver, Mars Magma, and Neptune Blue, and is refillable. Just as Earth's axis is tilted at 23.5 degrees relative to its orbital plane around the Sun, the Novium Interstellar is at 23.5 degrees, making it easier to pick up. The meteorite-embedded Space Black edition features a fragment of the Muonio Luster meteorite confirmed by a stainless steel certificate, meaning you'll have a piece of the oldest known meteorite on your desk. Of course, if you or your special someone prefer a fountain pen, then there's also the Hover Pen Future, which can be ordered as a fountain and rollable 2-in-1, or just as a fountain pen. If you're looking for a holiday gift or just want one for yourself, there's links in the description below, and you'll get 15% off for the next 72 hours by using the code PBS.
Damn, bro, you're level 676? That's crazy.
Yep.
Dude, I low-key kind of feel bad because I didn't know you were just a chill guy, and I was like pushing you. Oh my god.
No, yeah, I was straight up chilling. I heard you come by, and I was like, oh, man.
I lost you for a second.
No, you pushed me hard. How many shockwaves did you have? I didn't have any other than the base ones.
I had 6 in my inventory.
Yep, I had like nothing. I got nothing in that game.
What percentage are you?
Good question. $25.
Oh shit. Okay, I'm 98%, so I'm like right there. This next game should do it. So do you like usually just like what do you do? What's your playstyle?
It depends. I mean, usually I'm kind of competitive and ranked, but I don't know. For the past few games, I was just chilling. I was gonna hide the whole thing and just wait till the end.
I feel you on that. We can do that, Loki. I'm so down for that.
Yeah, I'm down for whatever.
Right, but
Where's your favorite
that's
land
how I
spot?
usually play. You said what?
Where's your favorite land spot?
I usually just go to any blue spot.
That works.
So we could go Riptides. But yeah.